Before we talk about how to find the phase angle of the steady state using, again, that same analysis that we had before, saying that we can really just get it from the polar form of our undetermined coefficient of the complexified differential equation. Cats are going wild today. They're excited to learn about math. Before we do that, I want to briefly review something we did in the last video where we talked about the relationship between a complex number and its reciprocal. We said if we have any complex number, the reciprocal of that in polar form would just be the reciprocal of the modulus and then the negative angle. So specifically, if this was some angle theta, this was just some angle negative theta, is what we said. And I want to look at that a little bit more before we get into the phase angle. So we'll have a little bit of bonus complex analysis. The cat just spilled water all over the floor. It's fine. It's fine. So this is going to be our real axis. This is going to be our imaginary axis. And let's look at a complex number. Let's say we're looking at the complex number negative root 3 plus I. Now, hopefully I've set this up to be a nice example. Otherwise, that'll be a little awkward. But that means that the imaginary part is just 1. And the, oh gosh, I've already messed it up, right? No, it's fine, it's fine. And the real part is negative root 3. So by quick Pythagorean theorem, right, we know 1 plus 3 is 4, square root of 4 is 2. Great. And specifically, we see that this is a 30, 60, 90 triangle where it's, hold on, figure maybe not drawn to scale, but I think it is, right? This is 30 degrees right here, which means that this angle over here is 150 degrees, and we know some things about this. So my claim to you is if we look at the complex number 1 over negative root 3 plus I, this complex number should have an angle of negative 150 degrees. It will not have the same modulus. It'll have the modulus of 1/2 actually. So my claim is that if we graph the other complex number, it's going to have a quarter of the length, right? Instead of 2, it's going to be 1/2. But it's going to be just the negative angle. Well, let's see if that's true. How do we simplify this complex number? We multiply it by its conjugate, negative root 3 minus I, negative root 3 minus I. When we do that, the top is just negative root 3 minus I, and the denominator is positive 3 minus I squared, which is plus 1. And what we get is a quarter. Interesting that we get a quarter. Let's actually write this as negative a quarter root 3 plus I. Notice anything? Noticing here that yes, the length is going to be a quarter of the length of before. The length will be a half when you do out the math. And specifically, look at where this complex number is. Maybe I should distribute that negative, right? Negative, negative. They're both negative. It's in the third quadrant. Has the same size of the real part. Well, it has the same direction, right? They have the same ratio. They're similar triangles, just in the fourth quadrant. Yeah, we could find the angle and it'll be negative 150 degrees. So there's just a little example to show you why this is the case. That for A, which is going to be the amplitude times e to the I times the phase shift, and B, which is going to be have some other modulus and some other angle. And remember, we said that A was 1 over B. B we made up. We said, I'm going to introduce a new letter for the complex number B just to make my life easier. And A is going to be all this. We're just saying B is going to be the denominator. So A, by definition, is 1 over B. Well, we know the relationship between all these things. The amplitude is just going to be 1 over the amplitude of B's, which we already found out before. And the phase angle is really just going to be the opposite of B's phase angle. So if I want to find the phase angle of the steady state, all I need to do is to find the angle of B and take the negative. So what was B? If you remember, B, I don't remember. B was Q minus omega squared plus I times P omega. Okay, so this is the real part, and this is the imaginary part. I'll say this a million times. Remember, the imaginary part of a complex number is real. The imaginary part does not include the I. Okay? So if we wanted to find the angle of a complex number, it's just trigonometry. The angle of a complex number is just given with sines and cosines. Well, specifically tangent, right? Because we have the imaginary part as the opposite and the real part as the adjacent. So we know that the tangent of B's angle, which we'll call theta, is going to be the imaginary part over the real part. Right? Using the same logic that we had over here. Again, this is just imaginary part, and that's just the real part, just opposite over adjacent. And furthermore, we know what quadrant theta is in. Right? Because the real part could be positive or negative depending on how big our spring constant is. The real part could be positive or negative, so we don't know whether we're to the left or the right. But the imaginary part we do know. Specifically, this is the coefficient that comes from damping. This is just the damping coefficient divided by the mass. It's something non-negative divided by something positive. And specifically, we're going to only look at the damped case right here. So we know this is going to be positive. The frequency we're making to be positive. It could be negative, but then we would just change things and have a negative somewhere else. So we can take this to be positive. So the imaginary part's positive. We have to be up here. We have to be in the first or second quadrant for B as a complex number. So the angle relating to B must be an angle in that first or second quadrant. It's going to be between 0 and pi, or 180 degrees if you want to use degrees. It's fine either way here. We've used both. And so that's really nice because, again, remember the relationship between our phase angle and the angle of our denominator. Because, as we said back here, A is just the reciprocal of some other complex number that we called B. The angle of B, we know. The angle of A is just going to be the negative of that because of how reciprocals work for complex numbers. So if that's the case, phi is going to be between negative pi and 0. It's going to be the opposite of theta. So we can put all that together. We know this is the equation that defined theta. We know phi is just going to be the opposite of theta. So we know our phase angle of our steady state. So we'll say the tangent of phi is negative p omega all over q minus omega squared. And we're looking for the phi. That's between negative pi and 0. That's going to be important. And there's a couple of very natural questions here. First off, why do I have a negative on the right-hand side instead of a negative right here? I said phi was negative theta, so shouldn't the negative have been here? And it was. Tangent's an odd function. So negative on the inside is the same as the negative on the outside. I just multiplied it over. Okay? So really there was a negative here when I was looking at phi, multiplied it by both sides. And then also, why don't I just use arctangent? And the answer is, remember what arctangent does. Arctangent always gives you an angle between negative pi over 2 and pi over 2. That's not what I wanted, because that's not what we had up here. We didn't have an angle between pi over 2 and negative pi over 2. So we couldn't really use arctangent. We said it needs to satisfy this equation. We're looking at this. We could create a different kind of arctangent, but because if you remember, arctangent was really just what happened when we restricted the domain to something arbitrary. We just forced it to be one-to-one in a somewhat arbitrary way that we found convenient. So there are other ways of defining inverse tangent functions if you wanted to, but this is how we're going to find our phase angle. So for example, you know, and there's really a lot to say here, and I don't want to talk forever about it. All right, if I found out, if I plugged in different values of p, omega, and q, and I found out that the tangent of phi needed to be root 3, for example, we'd just go and we could calculate this by hand, and we'd choose the one that was in this area. So we'd remember our special triangles. I don't expect anyone to have trig memorized. If you do it enough times, sure, you'll have it memorized. But all I need you to remember is your two special triangles, and that's much, much easier. 45, 45, 90, and 30, 60, 90. When is the tangent going to be root 3? When is opposite over adjacent going to be root 3? The answer is right here. That's a 60-degree angle, pi over 3. But again, we don't want pi over 3. So, right, pi over 3 is an answer to this, but we don't want that answer. We know tangent has a period of pi, so we could get into this range by just subtracting pi from this. So our answer would be negative 2 pi over 3. That is how we would find our phase angle if we were solving it like this. Okay? So, brief review there. Let's see what this behavior looks like when we graph it. So I showed you how omega, p, and q all interact to find the amplitude. Well, let's see how omega, p, and q all interact to find our phase angle. And again, disregard this stuff up here, and also disregard the stuff down here, because we're only looking at a phase angle between negative pi, which is down here, and 0. Right? We're only looking at a phi that's between negative pi and 0. So even though I'm graphing something that's implicit, so there's going to be infinitely many copies, this is really only what we're going to look at. And similar to before, q is not very interesting. Varying q is just kind of a horizontal change here. So let's just pick a q and run with it. Okay, maybe q can be 2 because that rhymes. Now we can see, how does adjusting the damping coefficient change this? Well, if the damping is pretty high, then if the damping is relatively high, then we can see the relationship between, and again, what am I graphing? I'm blocking it again, blocking the label of our axis. But here we're graphing, the input is our forcing frequency. The horizontal asymptote is our forcing frequency, and then the output is going to be our phase angle. So how does the forcing frequency affect the phase angle? Well, if you have high damping, then what it would appear is nothing crazy is happening if you have higher damping. If you have higher damping, though, we do notice that the phase angle is bigger, in magnitude anyway, right? So there's more of a difference. For this level of damping, for higher damping, there's not really that much interesting, but we can see that for a higher forcing frequency, there's more of a disconnect between the forcing function and the forced response. Because that's what phi is, right? That's what the phase angle is. It's how because if you remember, and hold on, there's really a lot going on here, sorry. So if you remember, right, we have our forcing function, which is just looking like this. This is our forcing function. But we also have our forced response, which is in this form. This is our steady state behavior. And you can see, right, that they have the same frequency. They have the same forced frequency, the forcing function. Think of the oscillations of you shifting a table, or the swaying, or not the swaying of a building, but maybe like if you had harmonic oscillation from an earthquake or something like that. The external force has some frequency, and that will always be the same as the forced response frequency. But they might not be in time with each other. They might not be in phase with each other. And that's where phi comes in. Because if phi is equal to 0, then our forced response, our long-term behavior, is really oscillating in motion or in sync with the forcing function, with that external function. But the bigger phi is, well, up to a certain extent. Remember, phi is only going to be between 0 and pi, because as soon as phi is bigger than pi is half a period away. So as soon as phi is bigger than pi, it's really just kind of like a backwards, like we're now closer just in the other direction. So that's one way of seeing why that connection happens. Okay, so we're really going off the rails here, but remember, phi is just, are we in phase with the forcing function, or are we like desynced with the forcing function? And you can see that for high damping, nothing that interesting happens, and the bigger that the forcing frequency is, the more out of sync or out of phase our forcing function is with our forced response. But more interesting things happen. Look at what's happening as our damping goes down. It actually becomes less smooth. Look at that damping. As we get closer and closer to an undamped harmonic oscillator, you see some very interesting behavior. Specifically, if the damping gets really, really small, then what happens is that the effect of the forcing frequency is either very little, oh gosh, we can't trace, right? Over here, changing the forcing frequency, we're still basically in phase with the forcing function, right? Changing the forcing frequency, different forcing frequencies, we're still in phase. But then really quickly, as we get close to probably that, oh yeah, this is about the square root of 2. As we get close to that natural frequency, the phase angle changes really rapidly, and specifically it changes really rapidly to get really close to pi. So we start off as being completely in phase, and then for minimal damping, as that forcing frequency gets close to the resonant frequency, we get a really rapid change centered on pi over 2. And then we eventually turn off to be very quickly get like half a period off from that forcing function, which is pretty interesting. Okay, so in summary, here is how we find the phase angle. We have to solve this equation, making sure that we take the phase angle in the right area. And again, any phi would work here. It's really kind of just convention that we're looking at phi here, because you know all these are periodic functions. But this is really the convention. A couple of quick things. I know this video has gotten very long. I've gotten very excited. A couple of quick things remember that the phase angle is not the same thing as the phase shift. if I look at something like this, this is the same thing as a cosine of 2 times x minus a negative pi over 2. So pi, this is the phase angle. Okay, but negative pi over 2 is the phase shift. So if you remember back to your trigonometry days and plotting phase shifts, they're not quite the same thing. This doesn't exactly mean that we're moving it left pi. I mean, it kind of does. We're moving it left pi and then we're compressing it. But usually we think of things as compressing it and then moving it left pi over 2. Okay, so phase angle and phase shift are very closely related, but they're not exactly the same thing. And then I do want to write down one of the conclusions that we verbally stated as well. It'll be a little easier to write things down. So if omega is large, and when I say large, what I really mean is omega is bigger than the natural frequency. If omega is large, then our phase angle, we saw that. Our phase angle approaches, and this is for any damping really. We just have to be much larger if we have more damping. So, so it's either greater than the natural frequency or much greater than if we have more damping. If we have damping, we really need much greater than. So if omega is large, then this approaches negative pi. And specifically, what that means is that our steady state is essentially half a period from our forcing function. We're out of phase. Like almost opposite for out of phase. But if omega is small, which would be when omega is less than the natural frequency, and again, if there's damping, it really needs to be much, much less than this. What happens, what did our phase angle do if our forcing frequency was really small? And again, you can see this much more easily with low damping. It was almost 0. And specifically, our steady state was in phase with the forcing function. All right. So that's a ton. Here's how we calculate it. And then we did a lot of analysis. A lot of cool ways of seeing things. Let me know if you have any questions. And in the next video, it's on the other page, I don't remember, we introduced 2 more parameters. This was only 3 parameters. Now we're going to 5 parameters. What's going to happen? It's going to be really easy, actually. So don't get scared. You've already done the worst of this section. Adding more parameters, in our case, is not going to make things very bad. We'll talk about what happens if we have sines. We'll talk about what happens if we have higher amplitude forcing functions or phase shifts on our forcing functions, and it won't be bad at all. You've got this. I'll see you there.